So technically, at this moment, I'm one of those unaffiliated mathematicians who work from home. But that said, the bulk of this work is done at the University of Helsinki jointly with Jonas Turunen, who was a PhD student there. And by the way, he will defend in 2 days. Okay, so today's talk will be about the Ising model on a random 2D lattice. So the structure of the talk will be in two parts. So the first part, I will introduce the general context of the problem. And this part will contain introduction to the Ising model and to what I mean by a random 2D lattice. I apologize to those who are already familiar with this concept. So if you get bored in this part, you may maybe come back at the end of like 20 minutes. And in the second part, I will introduce some recent results that I obtained jointly with Jonas. Okay, so first, the Ising model is a model from statistical mechanics defined on a finite graph. So here we will consider a graph G embedded in the two-dimensional plane. And the model also comes with a coupling constant, which is positive. And here we will consider the nearest neighbor Ising model on the faces of the graph G. So here is a drawing. And a configuration of the Ising model is a assignment of the number plus 1 or minus 1, which we call spins, to the faces of the graph G. So a configuration is just a set of numbers plus 1 or minus 1. And we choose randomly these configurations with a probability that is proportional to the coupling constant nu to the power of this number. So this number is the number of faces x and y, which are adjacent and which have the same spin. So in the following, I will denote this number by EG of sigma. Some of you may be more familiar with the Ising model defined on the vertices of a graph. But in 2D, these are really the same problem, because when you have a graph G embedded into the plane, it automatically has a so-called dual graph, which exchanges the role of faces and the vertices. So the model that we are considering is just the usual Ising model on the vertices of a graph, but for the dual graph. And for those of you who are familiar with the familiar with the definition of the model in the physics literature, the coupling constant nu that I'm using here is related to the bound energy E and the temperature T in this manner. So what is important here is that nu is a decreasing function of the temperature T. So large value of nu correspond to a low temperature, and small value of nu correspond to a high temperature. And usually the Ising model is studied in the ferromagnetic case, which means nu larger than 1. And also in the case where G is a subgraph of a regular 2D lattice, that is a triangular, square, or a hexagonal lattice. So in this talk, I will remain in the ferromagnetic case, but I will change the second setting by replacing G by a random graph. So the initial motivation to study this model is that it is a very simple model, simple yet rich model of a ferromagnet. describe a sort of classical competition between order and disorder in statistical physics. So basically, the weight of the spin given to the spins tend to align the spins, that is, make all the spins have the same value, while the disorder tend to misalign the spins. And maybe more important for mathematicians, the Ising model is one of the simplest model, which is at the same time mathematically tractable and also demonstrate the existence of a phase transition. So what is a phase transition? So here I give the typical configuration of the Ising model at 3 different temperatures obtained by simulation. So on the left, I have the typical configuration of the Ising model at high temperature. And as you see, the spins are more or less randomly distributed. While on the right-hand side, I have a typical configuration for low temperature. So here the configuration are the boundary spins of the configuration are imposed to be red on the lower half and blue on the higher half. So so the tendency of the spins to align to each other create an interface in between and 2 large chunk of aligned spins. And what is more interesting is what happens in between these 2 cases. So there is a critical temperature at which the spins are kind of mixed, but you have islands of aligned spins at all scales. So and one might ask, even if this model has a rich behavior, it's an extremely simplified model for any physical system, and we would not expect any real system to obey the same law on the microscopic scale. So the spins in atoms don't interact exactly in this way. So what good does this model has to model the real physics? Well, one part of the answer lies in the concept of universality. So universality is the phenomenon that some macroscopic observables of a statistical physics system at or near criticality is independent from the microscopic details of the system. And here I emphasize on some macroscopic observable. So not all observable are behave this way. There are non-universal observables which depend on the details of the model, and universal ones which do not depend on the detail of the model. For example, this temperature nu c is a non-universal observable. If you change the underlying graph of the model, this temperature will change. But later we'll see examples of universal observables. So then in general, how do you describe a phase transition mathematically? So without relying on drawing pictures. So first, the definition proposed by the physicist is that the so-called free energy density of the system. So free energy is the logarithm of the partition function, and density just means that we divide by the size of the system. So this function, when the size goes to infinity, will be non-analytic at the critical temperature. So this is what one signature of the phase transition. Another signature of the phase transition comes from the so-called correlation functions. So for example, if you look at the spin in the model at the origin and the spin at a distance x from the origin, and you look the correlation between these 2 spins, it will decay exponentially when x goes to infinity if the temperature is not critical. And but it will decay polynomially when the temperature is critical. And higher order correlations also behave in this way. And actually there is a very rich theory called the CFT, so conformal field theory, that describe the behavior of this all these correlation functions at the critical temperature. And finally, we can also look at more geometric observables, such as the probabilities that different parts of the boundary are connected by spin bridges, or the interface between regions of different spins. And in the large scale limit, this leads to random geometric objects, such as the so-called SLE. But I will not enter into any detail of this continuous theory, CFT or SLE. And I guess there are, so I will rather focus on a relatively discrete scale of the model. So a very simplified history of the Ising model. The model was first proposed by Lenz in the 20s. And his student Ising worked out the one-dimensional case and found no phase transition. But later, Onsager computed exactly the partition function of the model on the 2D square lattice and obtained the critical temperature. And this was followed by more exact computations and the values of so-called critical exponents of the model. And in the 80s and 90s saw the development of the theory of CFT that was mentioned above. And by the way, up to this point, the work are largely done by the physicists. But in the 2000s, mathematicians start to catch up and start to prove some of the convergence results predicted by the physical theory of CFT, and also came up with geometric objects like SLE and CLE, and show that they are effectively the scaling limits, interface scaling limits of the Ising model. Okay, so next I will try to explain what I mean by random 2D lattice. So this may be a part which is less familiar to most of you. So the technical term for random 2D lattice is random planar maps. So a planar map is just the embedding of a finite connected graph into the sphere, into the two-dimensional sphere without crossing edge. So basically, a random map is a planar map is a planar graph with an embedding. So you can imagine this like a furniture from IKEA. So basically, it contains not only the components that you need to build your graph, but it also contains instruction for you about where you should put the edges of your graph. So here I give an example of, I give 3 pictures of the same planar graph, but the first 2 represent the same planar map, while the third one represents a different planar map. So the reason is that by deforming continuously the edges without crossing them, you can never move this vertex from outside to inside. Another way to see that the later 2 examples are different is that you can cut the paper along the edges of your embedded graph. Then you see that in the left graph, you have 2 faces which are triangles, and an outer face which is of degree 6 or a deformed hexagon. while on the right-hand side, you have one triangle, one pentagon here, and outer face of degree 4. So clearly they are different when embedded into the plane. And to avoid a symmetry problem, we will usually mark a corner of the embedded graph, which we call the root. So, but for today's purpose, you can more or less think it as a marked vertex. And by convention, we'll always draw this marked corner on outside of the picture. And the planar map with this marked corner is called a rooted planar graph. But in the following, I will just say map instead of rooted planar map. So some terminologies. So first, the external face is just the face that contains the root. So, and in all my pictures, it will effectively be the face which is drawn on the outside. And the internal faces are just the remaining faces. So here there are two internal faces. And the boundary is just what you would expect, the edges and the vertices on the external face, and the perimeter is the degree of the external face. So for example, here you have a perimeter of 6, and here you have a perimeter of 4. And moreover, we call a map a triangulation if all of its faces are triangles. And if only the external faces are triangles, then we talk about triangulations with boundary. So for example, here, this one is a triangulation with boundary. Okay, so I hope the definitions are clear. So, well, here are some larger pictures, larger examples of planar maps. So the first one is a planar triangulation. The second one is what a so-called quadrangulation. So basically, you replace triangle by faces of degree 4 and with a boundary. And here you have a more general planar map with boundary and without constraint on the degree of the faces. And once we have these deterministic planar maps, we can put randomness on this object. So a uniform triangulation of size n is just a random element chosen uniformly in the finite set of all triangulations with n faces. And what I will call a Boltzmann triangulation is basically you relax the constraint on the size of a uniform triangulation, and you replace it with this probability of choosing a triangulation. So the probability of choosing a triangulation is some parameter t to the number of its faces. So basically to the power of its size. Okay, and then we can define a partition function of the Boltzmann triangulation by summing over all possible finite triangulations, and we sum this weight over all the finite triangulations. And it can be written also in this way. So if Tn is the number of triangulation with n faces, then this partition function is just the generating series of this sequence of the number Tn. Okay, so one nice thing about a random planar map is that the counting of these objects is relatively simple and now largely understood. And for example, the number of triangulations of size n have this asymptotic formula. So you have a constant factor and exponential decay of the or here I guess it's rather exponential increase of the number, so TC is smaller than 1. And then you have a polynomial factor. And here I emphasize on the exponent 5/2 because this will be the exponent which is universal among all the planar maps. By universal, I mean that if you look at not triangulations, but other classes of planar maps with some notion of size n, then basically their number are asymptotically counted by the same formula, but with different values of the constants C and TC. But the point is that you always get this exponent 5/2 in your counting formula, even if you change the class of planar maps that you count. And I would like to compare this counting formula for planar maps to the counting formula of the so-called plan trees. So basically, these are trees that are drawn, are embedded, which are embedded in the plan. So for these trees, you have a very similar counting formula, except that the exponent, instead of 5/2, you have 3/2. So this gives this gives the example of two so-called universality classes. So basically, all the random planar maps form a universality class in the sense that when you count them, you always get this exponent 5/2, and or let's say reasonable models of plan trees always give this 3/2 in their counting formula. And well, having an exponent is nice, but the question is, are there other universal observables? And the answer is yes, and actually a lot of them. So for example, one way to summarize this large number of universal observable is can be done using a theorem of Aldous in the 1990s. So he has proved that if you look at a random tree of size n, choose uniformly from, well, one of many reasonable classes of rooted plan trees. And if you look at this tree and you look at the graph distance on the tree, and you renormalize the graph distance by this factor, and then this couple viewed as a matrix space, a discrete matrix space, converges when n goes to infinity to a continuous matrix space, and weakly in I guess just in distribution with some topology that I will not explain here. And the point is here is that this continuous matrix space does not depend on the class of rooted plan tree that you choose. And so any observable that you can read from this continuous object will be a universal observable for the universality class of plan trees. And a similar theorem now exists for the for random planar maps. So if you choose a uniform random planar map from one of many reasonable classes, and you renormalize the graph distance on these random planar maps by this factor, then the couple viewed as a matrix space when n goes to infinity will converge to a continuous matrix space, which is called a Brownian map. And we also know some of its properties, such as its Hausdorff dimension and its topology. So here are just some computer simulation of the limit objects that are obtained by people. Okay. And also a very simplified history of the theory of planar maps. So in the 60s, the theory started with the enumeration, with works on the enumeration of planar maps using combinatorial methods done largely by Todd and his collaborators. And in the 70s and 80s, physicists came up with different ways to encode planar maps by either Feynman diagrams or matrix integrals, and developed more tools to compute their partition functions. And also, they realized that planar maps can be viewed as a discretization of the so-called Liouville quantum gravity, which is a theory of gravity, well, a theory of quantum gravity. And in the 2000s, saw the discovery of some bijections that encode planar maps by simpler objects such as trees, and this allowed people to study more geometric properties of these random graphs, and which finally leads to the construction of the planar map, which was the object in the previous limit result. And then one question is that, well, having a universal limit object is nice, but is there a way to create other universality classes? And the answer is yes. One way to do so is to not choose the random planar maps uniformly from a class, but choose it with a probability that is proportional to the partition function of some statistical physics model that lives on the map. So as you might guess, today I will talk about the choice, which consists of weighting the planar maps with the partition function of a Ising model. And so in this direction, previous works are relatively sparse, but here you have a couple of them that laid foundation for at least for the enumeration of these weighted planar maps, but we are still at the level of enumeration, and the geometric objects of these weighted planar maps are largely to be explored at this moment. Okay, so now I will get into the second part of my talk. So I will start by introducing the model that I studied with Jonas in our recent work. So the definition of the model starts with what we call a Ising triangulation of the disk. So these are objects built on a triangulation with a boundary. So here with a simple boundary, but that is just a technical condition. And moreover, we split the boundary of the triangulation into two intervals like this. And I call the length of these two intervals P and Q. And then I will put an Ising model on this random triangle on this triangulation. So I assign +1 and -1 to each face of the triangulation, and also I assign a boundary condition to each boundary edge. And in this talk, I will focus on the so-called Dubrusian boundary condition, which basically assign a spin plus in the first interval of the boundary and a spin minus to the second interval of the boundary. So I will call the set of this triangulations with boundary condition and with spin configuration on them. I will call the set of all these objects IT plus minus. So basically Ising triangulation with a plus minus boundary condition. And as before, ET of sigma will denote the number of monochromatic edges in this in each of these configuration. So recall that this was the quantity that was used in the definition of the weight of the Ising model. So for example, in this example, of course, I have a plus boundary of length 2, a minus boundary of length 3, and I have 7 faces if you count. And also the number of monochromatic edges, which are marked in yellow, is 5. So I count also the boundary edges here. Okay, and as mentioned, a large part of the study of these weighted triangulations are still very much on the level of enumeration. So I will start by defining the generating function or counting series of these objects. So basically, I will just use a series with a power series with 4 variables that collects the 4 quantities that I gave in the previous example. So u to the power p, v to the power q, etc. And here nu is the coupling constant of the Ising model. And here are just some notations that extract one or both of the coefficients in this previous series. And so given a pair p and q and a set of parameter t and nu, if this coefficient zpq is finite, then we can define a probability measure on the set of these Ising decorated triangulations with a fixed boundary length p and q. So p boundary with spin plus and q boundary with spin minus. So if this number is finite, we can renormalize the weight by this number and define a probability distribution. And a random variable with this probability distribution will be a Boltzmann-Ising triangulation, and that is the random object that I'm interested in. So it comes with a fixed pair of a fixed boundary condition. But basically the idea is that you generate randomly the configuration of the Ising model and the underlying graph at the same time, and their joint distribution is controlled by this weight here. Okay, and this the symptotic behavior of the coefficients of this partition function has already been studied before. So here I don't want to enter into the detail of the content of this theorem. I just want to mention this theorem because it gives us a hint about where the phase transition occur in this model. So these authors, they have looked at the asymptotic of the coefficient of this series in the variable t, and they discovered that this asymptotic have two different behaviors depending on whether the coupling constant or the temperature is equal to some particular value or not. So this is a strong indication of the fact that there is a phase transition that occur precisely at this value of the coupling constant. And some easy corollary of the previous result is that, for example, TC is the radius of convergence of this this series. And moreover, if you plug T equal to TC into this series, then it is the series is convergent. So basically, this series is convergent on the boundary of its Discover convergence. And also, if you take the logarithm of the coefficients of the coefficient here and you divide it by n, so recall that ZPQ is basically the partition function of this model with fixed parameter P and Q. And N is basically the volume of the model. So log the partition function divided by volume is the free energy density. So this gives you this function. And according to the previous theorem, this free energy density has precisely 1 point of non-analyticity, and this point is at nu c. So it's another way of saying that there is a phase transition at nu c. And in the following, I will focus on the case where I fix the parameter t to its maximum value. So recall that Tc is the radius of convergence of this series. So I cannot plug in any value larger than Tc, otherwise I'll get infinity. But I'll plug in the maximum value. And also I'll focus on the ferromagnetic case where the coupling constant is larger than 1. And so for this reason, I will not write parameter t anymore in the rest of the slides. Okay, so I hope the model is clear. So these are the partition functions again. So now the results that we obtained. So first, if we define UC as the radius of convergence of this series, so basically it's the series ZUV, but with V equals 0. And we can compute this radius of convergence quite explicitly. And we find that it is positive and continuous on for all nu larger than 1, and also analytic everywhere except at nu c. So this is another indication of the phase transition at nu c. So I'll explain later why I call this thing a surface tension. And more precisely, if we look at the partition function ZPQ of nu, so recall that t is fixed at Tc, so I no longer write it. And when q goes to infinity for some fixed value of p, and then p goes to infinity, so I'm taking two consecutive limits. Then we have the following asymptotic of the partition function. So the asymptotic has the Euro form of a constant times an exponential term times a polynomial term. And if we look at the constant and we only the constant depend on the parameter p, and if we look at this constant and let p goes to infinity, it also has a asymptotic of a similar form. And next, we can also look at the limit where pq goes to infinity at the same time, while q over p tends to some fixed positive parameter. And we obtain a asymptotic of a similar form, where the value of the exponents are given in this table. So, and the constant here can also be written down explicitly. So here I would like to emphasize the fact that even though our partition function depend on a continuous variable nu, the exponents alpha 0, alpha 1, and alpha 2 only depend on the phase in which the value of nu is in. So it has a fixed value for all value of nu that is smaller than uc, and for all value of nu that is larger than uc, and it takes some other value when nu is equal to uc. So again, a sign of phase transition at uc. And in the following, I will more focus on these exponents. So here is a graph that will be useful later. So basically, well, it's not a very interesting graph. It's just a graph of a piecewise constant function. So alpha 2 goes up at nu c, alpha 0 remains constant, but somehow jump to a different value precisely at nu c and come back to the constant value afterwards. And after alpha 1 also jump up at nu c. And just to mention why I call this uc of nu surface tension, because it's basically the log of the partition function divided by the perimeter of the system, and this is what physicists usually call a surface tension of a statistical physics model. Okay, so this theorem gives the asymptotic of zpq of the partition function for a fixed temperature. And the next result, in the next result, we look into the so-called near critical regime, where we relate the coupling constant to the perimeter of the system, or roughly to the size of the system. In this manner, so they have a polynomial. This is a polynomial function with a exponent beta. And we look at the same limit regime as before. So q goes to infinity with fixed p, and then p goes to infinity, or pq goes to infinity at the same time with the ratio goes to some constant. And then we have, again, some asymptotics which are quite similar to the previous ones. But this time, the exponent, instead of piecewise constant, it becomes a function of this parameter beta. And here I draw the graph of this exponent with respect to the parameter beta. So here, the graphs are drawn somehow in a strange way. So for nu, so of course, this relation only, for a given value of p, this relation only gives the absolute value of nu minus nu c. So you also need to specify whether nu is smaller than nu c or bigger than nu c. So when nu is smaller than nu c, the exponent depends on beta in this manner. So the exponents are piecewise linear constant with this, and whose values are determined by this particular point. And when nu is larger than nu c, I draw the coordinate system somehow in the mirror, but the exponents are also piecewise linear constants. Sorry, piecewise linear functions. And the reason that I draw the graphs in this strange manner is that in this way it can be conveniently embedded into the graph that we saw on the previous page. So on the previous page, we say that these exponents are piecewise constant functions, which jumps suddenly at nu c. And so what we have here is basically a graph which zooms into a neighborhood of nu c and tells us how this exponent change gradually as we get closer and closer to criticality. So as you see that this solid line interpolates conveniently between the graph on the previous page. Well, the green graph is somehow different because here we are not taking the asymptotic of this coefficient, but we are taking the asymptotic of a different variable. So the alpha 1 does not really fit in. And also one comment on the limit regime that we were taking here. So if you imagine our model with Ising model with a diverging boundary condition, so P and Q are the parameter of the plus boundary and minus boundary. So basically the first limit here is saying that I look at my finite parameter and I send first the number of minus boundary edges to infinity. So basically I'm unfolding the minus boundary to an infinite line, and what I obtain is an infinite boundary with a minus boundary condition almost everywhere, but except a finite segment of length p, which has a plus boundary condition. And so from a physics point of view, it's a somewhat strange limit to take. But the second limit is much more plausible. So here I'm sending both the plus boundary and minus boundary to infinity, and at relatively at a similar speed. So in this second limit, we can it makes more sense to rescale this the system down by the parameter p and look at some kind of scaling limit of the system. Okay. So so I think I'm running out of time. So I'll try to be quick for. Well, I guess I'll skip this local limit part because anyway, I just want to say that this is not the most interesting part of the result, but instead I'll try to explain more the scaling limit result that I obtain. That we obtain based on the previous enumeration result here. So so if I call LPQ of nu the length of the leftmost Ising interface that goes from row to row prime in a Boltzmann-Ising triangulation. So, so recall that row and row prime are the 2 points on the boundary of the Ising triangulation, which separate the minus boundary from the plus boundary. So the boundary condition basically force one macroscopic interface between these 2 points. But here, since we are considering the model on the faces of a triangulation, this the interface in this model may branch. So it's not a curve, but it has a lot of branch points. But if we look at the leftmost Ising interface, and of course the rightmost is the same by symmetry. And if we look at the leftmost interface and we look at the length of this interface, then in the limit, so in the physically relevant limit where PQ goes to infinity at a similar speed, we obtain the following result. So if nu is larger than nu c, so when the temperature is low, the interface scales linearly with respect to the perimeter, and it converges in distribution to 0. Well, actually, it does not scale linearly. It's much smaller than the perimeter. While if the coupling constant is smaller than nu c, so at high temperatures, it's the interface length scale this time scales linearly with respect to the perimeter and converge to some deterministic constant. And finally, if we are exactly at the critical point, then the interface length actually, much to our surprise, also scales linearly, but this time it has an interesting random limit with whose distribution is given by this this density, whose distribution has this density. So to summarize, at all fixed temperature, the interface length scale at most linearly with respect to the perimeter, and it converts to 0 at low temperature, to some deterministic constant at high temperature, and to a random, a finite random variable at the critical temperature. Actually, for the near critical regime, we are still working on it. But what we believe that should happen in the near critical regime is that there is some funny cutoff at the high temperature case. So for nu smaller than nu c, and at the parameter value beta equal to 1/3. So on one side of this this cutoff, the interface length scales as the perimeter to some exponent which is between 0 and 1, and which can be computed using our enumeration results before. And moreover, after rescaling by this factor, we believe that the interface length should converge to some non-trivial random variable supported on 0 infinity. But we haven't worked out the distribution yet. On the other hand, on the other side of the cutoff, the behavior is more like the high temperature behavior here. So the scaling is linear, and after rescaling, length converge to some deterministic constant that is larger than 0. So yeah, I just come back a little bit to the previous graph to show where the cutoff is. So recall that we have the cutoff at nu smaller than nu c and beta equals 1/3. So basically here. So what the last conjecture was saying that on the right of this cutoff, the parameter, sorry, the interface length behave kind of like in the low temperature regime. It scales sublinearly with respect to the parameter. And on the right of this cutoff, it behaves like in the high temperature regime, where it's basically proportional to the parameter. Okay, and so that is all that I want to say for today. So thank you for your attention.
Thank you very much. Let me thank you on behalf of the audience. Yeah.
And here are the papers
Yes.
that appeared in the talk.
Yes, thank you very much. And let me just remind you that the PDF slide with file with the lecture slides, with the talk slides, is available from the website for our seminar. So please feel free to download. Now,
yes, and also sorry, yesterday I realized that there was some typo, so I changed it a little bit, and also I added this reference. So maybe we can upload it, the newer version,
yes.
later.
Yep, we'll do it.
But there